Swastyastu, Assalamualaikum Warahmatullahi Wabarakatuh, Syallom, Namo Budaya, and good to see you all, guys. So now I will do some presentation about heat treatment of non-ferrous alloys. And my name is Shanti. I'm number and my college code is 2305531063. And our lecturer is Professor Dr. Sokorda Gede Tirtan India STMT MA. In this chapter and in this material we have metallurgy with the code TM2301, and I'm from Mechanical Engineering, Technical Faculty, Udayana University. In this presentation, I take my reference from module is called Metallurgy for Non-Metallurgy 2nd edition, edited by Arthur C. Reardon. And from the chapter Heat Treatment of Non-Ferrous Alloy, we got 8 sub-chapters. The first, recovery and recrystallization annealing, treatable aluminum alloys, and others. The heat treatment of non-ferrous alloys. Non-ferrous alloys are heat treated to tailor their properties for a variety of purposes, including aiding in recovery by reducing internal stress, promoting diffusion by redistributing existing alloying element, promoting new recrystallized grain formation, promotion grain growth, dissolving paste, producing new paste by precipitation from solid solution, altering surface chemistry by the introduction of foreign atoms, promoting new paste formation through the introduction of foreign atoms. Heat treatment also is used to strengthen some non-ferrous alloys. Strengthening of many non-ferrous alloys by heat treatment typically involves one of two metallurgical principles: the precipitation, hardening from the fine dispersion of second paste, precipitates that form in the metastable quench single paste alloy, as in Dr. Williams' mystery with aluminum copper alloys, and the two paste non-ferrous alloys such as titanium-based alloy and high zinc zinc alloys, where strength can be obtained with a mixture of two pastes of comparable quantity, unlike the two paste structures developed in precipitation hardening, where the precipitate is a minor component. We go to the first subchapter, is recovery and recrystallization annealing. Annealing is a generic term used to denote a thermal treatment process that consists of heating a material to an iron temperature and holding or soaking it for a sufficient length of time at the temperature, followed by cooling at suitable rate. When annealing is performed for short periods of time or at low temperature, the hardness of cold works alloy remains relatively constant. This initial stage is referred to as recovery annealing. Thus, some properties do change during recovery annealing. For example, the electrical resistivity of an alloy is typically increased by cold working but can be recovered before annealing has significant effect on hardness. Next, we go to the heat-treatable aluminum alloys. Brook and cast aluminum alloys are commonly designated by a serial originally developed by Alcoa. The series classified aluminum alloys by the principal alloying element. The highest strength level are attained by the heat-treatable alloys, which are strengthened by precipitation hardening as described in Chapter 3, Mechanical Properties and Strengthening Mechanism. In this book, the non-heat-treatable aluminum alloys include The next subchapter is cobalt alloy. Cobalt is useful in applications that make use of its magnetic properties, corrosion resistance, wear resistance, and/or strength at elevated temperatures. Biomedical application is another important use. In the edge-hardenable, cobalt alloys include two CO and CRMO alloys for corrosion resistance application. One is alloy MP335 and UNS R335 with a cobalt-rich composition 35% Ni, 20% Cr and 9.75% Mo, and balanced cobalt. Following cold work, precipitates of CO3MO form at platelet boundaries in MP35 and alloy during edge hardening. The other edge hardenable alloy is a more nickel-rich alloy with a composition of 36% CO, 19% Cr, 7% Mo, and balanced nickel. Next, we go to the copper alloys. Copper alloys can be hardened by solid solution alloying and by work hardening. The commonly used solid solution alloying elements listed in approximate order of increasing effectiveness are zinc, nickel, manganese, aluminum, tin, and silicon. An additional limited number of copper alloys can be strengthened by heat treatment. In the precipitation hardening copper alloys, edge hardening mechanisms are used in a few but important copper systems that include edge hardening beryllium copper alloys, edge hardening chromium copper alloys, and edge hardening Cu and ISE alloys. In the magnesium alloys, the basic of tempered designation used to design the various types of heat treatment of magnesium alloys include F as fabrication, O as inlay, recrystallization, H strain hardened, W solution heat treated, T2 alloy, T3 solution heat treated and cold worker, and with another one. Some example of significant hardening that does occur from precipitation include magnesium alloys, magnesium aluminum alloys, magnesium yttrium alloys, and magnesium zinc alloys. So as we can see in here, this is the graphic of magnesium aluminum alloys, and this is magnesium yttrium alloys and magnesium zinc alloys. So in the titanium alloys, are heat treated in order to reduce residual stress developed during fabrication, stress relieving, produce an optimum combination of ductility, machinability, and dimensional and structural stability annealing, increased strength, solution treating and aging, optimized special properties such as fracture toughness, fatigue strength, and high temperature creep strength. In the microstructure feeder of titanium alloys, generally two types of phase may be present in titanium alloys after heat treated. Primary, which persist through heat treatment as the remnant from prior hot working or processing. Secondary are also referred to as transform B, which is produced by transformation of B to a during or after heat treatment. And other non-ferrous alloy, heat treatable silver alloys, the precious metal including silver, behave somewhat similar to copper and nickel. The most important silver alloys are the silver-copper type. Copper is added to increase the hardness and strength of silver, while its effect on electrical conductivity is small compared to that of other additions. When silver contains 10% Cu, Cu is the most commonly alloys. Fine silver 99.9% Ag is used for electrical contact. Tableware is usually made of sterling silver or standard silver having 7.5% Cu. The treatable gold alloys. The gold alloy which find application in the jewelry setting, trade and in the dentistry generally contain silver and copper and sometimes zinc, nickel, platinum and palladium. The properties of considerable number of these alloys are altered by different phase change. The copper-bearing gold alloys are characterized by the occurrence of at least 2 transformations in the solid state. So that's all my presentation. I'm really apologize when I have something problem with my speak or in my presentation, and I will close with Om Shanti 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 Om. Assalamualaikum warahmatullahi wabarakatuh. Syallom, Namo Budaya, and see you guys.